So today it's Windows, which is probably a point of great interest to me. We've done a lot of study of how to hack Linux, but of course the target most people want to attack is Windows. And the main reason to study Linux is so you learn sort of the basics of how operating systems in general work to apply to Windows, which is more complicated. So let's talk about Windows. And here's the topics. Some of these we talked about, mostly in the other class, in malware analysis class we talked about these. We'll talk about how Windows software works, how Windows memory is handled, and some very strange Windows objects like DCOM. So Windows has an API, an application programming interface, and this means if you have a Windows program, it doesn't actually do very much directly. All it does is call Windows functions that are written by Microsoft to do things. So I want to open a window, call the Windows API, please open the window. I want to read the user input, call the API. So you're really just sort of choosing from a menu of options provided by Microsoft, and that's all you can do. When you're using an operating system, you're in their environment. You don't have any direct contact to the hardware. All you do is call Windows functions to do things. Now in Linux, you call this with int80, with syscalls. In Windows, you get there through what's called the API, which is implemented as a set of libraries. And so every process uses dynamic linking to the libraries. When you load your program, it then connects to libraries in memory. And the Windows API changes pretty often. And so here, for example, is an API call to make a window. You call create window EX. And then here's some parameters in here like the title of the window and other things here like the width and height of the window and whether it's going to have scroll bars and things like that. That's the kind of call you would make. And then it returns a handle to that window, which you can refer to later to do things like close that window or move that window. So the libraries are precompiled library code written by Microsoft, and they load as needed. And the reason they're called dynamically linked is because if one program loads a library, like it has networking, so it calls WS232, one of the networking libraries, then any other program that wants that will just connect to the same running copy of the library in memory. So they all share the same one copy of the library, which makes it load faster and saves memory, but it's also kind of unsanitary. It means one process can end up interacting with another in an undesirable way. So if you load a program here, here's one of the service hosts running in the background. You can just turn on the lower pane view of Process Explorer, and you can see all the libraries it's using. And every typical application is using just a lot of libraries. All right, so all these are portable executable files. That's the general format for all Windows software. exe and DIL files and some other extensions are all portable executable. They can be loaded on every 32 or 64-bit Windows version. And the portable executable format in the header lists all the libraries this program needs so it can load them when you launch the program. So you can see the import table in PE view. You can see here's Notepad. And so there's an import table, and you see here it is. It has advanced API, kernel 32, GDI, user 32, and so on. These are all the libraries used by Notepad. So there's sections of the file. There's the text section, which are the machine language instructions that execute. There's data, and iData has data has global variables. Here's import information, resources, and here's relocation data used to relocate it in memory for address space layout randomization. So relocation is important. DILs have a base address, so do executables for that matter, where they would naturally load. Now, if two programs try to load at the same base address, then one of them has to be moved. And so that's called rebasing, and that uses the relocation section, which lists all the absolute addresses that are referred to in this program that must be corrected if you relocate it. So let's try a Kahoot. Should have them ready to go here. 6A is here. All right. All right, so which file contains precompiled library code? Libraries, dynamic link libraries. All right. All right. What's the functions Microsoft provides to access the kernel? That's the Windows API. Good. All right. What's the format for all Windows executables? Yep. Portable executables, PE. They're not all EXEs. DILs are also PE files. All right. Which section is used for rebasing? Relocation, good. All right, which section contains the machine code instructions? The text section, which makes no sense at all, but that's the way it is. All right, which section contains icons? Yeah, those are resources. There's a product called Resource Hacker you can use to change the appearance of Windows games and such by messing with the resource section. All right, so imports are ways to enter the program. These are functions you use elsewhere, like libraries. So you import a library, then you use some of the functions in the library. Exports are entry points that you offer to the world to come into your program. So EXEs typically only have one export, the main routine where you start. Libraries typically have many exports because they offer many functions. So here's notepad.exe imports, and that's what we said before. It imports from advanced API. It calls all these API functions, then comsctl32, it calls this one, and so on. It imports a bunch of libraries, and for each library, it uses a bunch of functions. So that's the imports. Here's the exports from a DIL, and you'll see the export table just has a large list of things. Here's just the A's, and this whole screen is just the A's up to the ADs. There's a huge scroll bar. So this library, Advanced API, just has tons and tons of exports. So there are many, many functions offered by this one library. So this is a fairly common problem, especially in earlier versions of Windows. You try to run a program and it can't find a DIL because Microsoft did not contain a system which Linux has called the link count. So they don't keep track of how many programs you're using a library. In Linux, it keeps track of how many programs you're using a library, and when it falls to 0, it deletes the library. What Microsoft does is every time you uninstall something, it asks you, do you want to uninstall this library? And users have no idea what you're talking about, and randomly answer that question, and then some other program needs it, and it's gone. So anyway, when EXE launches, Windows hunts for the DILs, looking first in the current working directory and then elsewhere. So there's a DIL sideloading issue. There's two problems. One is sometimes DILs are not found and the program can't run. And the other is you can exploit Windows by putting in a fake DIL with the same name as the real DIL, and then it will get loaded in. And this is the most common way malware runs on a box. And we've been doing it in the latest lecture in the malware analysis class. We've been making DIL hijacking and DIL proxying attacks that do that. Stuxnet worked this way. Stuxnet was the American and Israeli attack on Iran, and it used 4 0 days, but the most interesting one was the link 0 day. You would have a folder, and as soon as you put it on something like a USB stick, and as soon as you open the USB stick just to draw this screen to show you what was on the stick, you were owned, because it had a DIL that loaded as soon as the icons appeared. You didn't have to click on anything or run anything. Just the process that draws this visible window on a Windows XP machine would run executable code on the machine. Now, Windows exe processors are all loaded into a virtual address of 400,000 in hex. And the relative virtual address is used to rebase DILs if they have to load in non-preferred locations. So you see a possible virtual memory address. This executable is really in 300,000, the other one's really at 500,000, but they both think they're at 400,000. They're just mapped to. So the internal memories they use think they're running at 400,000, and they just are remapped by the operating system to their real location. All right, so Ollie debug. You see code typically starts at 401,000. It's where the text section usually loads in Ollie debug. Unless the program has relocated its in memory due to address space layout randomization, every exe likes to think it's loading at 400,000. All right. Now the heap we've talked about. The heap is a place for temporary storage of memory, of data, which is reallocated, and a lot of vulnerabilities involve exploiting the heap, heap memory corruption. So you allocate some memory with malloc, and then you're supposed to free it afterwards with free, but if you are able to override a string variable in the heap beyond its limit, you can have an overflow and collide with the next heap chunk. If you double free, you can have a situation where you get to control a write operation and so on. There's a bunch of ways to exploit the machine through heap memory corruption. Windows uses many heaps. Each DIL sets up its own heap, and so the heap corruption attacks on Windows are much more complicated than heap corruption attacks on Linux. And then there's threading. One fundamental process of computing is the processor is very fast and everything else is very slow. Even RAM is very slow, and the keyboard and mouse and network card and hard disk are all much slower than the processor. So there's a fundamental problem on computers that a lot of the time the processor is ready to do something, but it's waiting for some slow device to cough up the data it needs. So to avoid this, they try to break every task into many little threads that can proceed independently. So if one thread is waiting for something, like hard disk or SSD to cough up some data, the other threads can maybe move forward while this thread is paused. So you don't waste so much processor time waiting for slow devices. So that's the game, and that's what threads are. And you can see them in Task Manager. If you go into modern version of Task Manager, it'll tell you there's 41 processes with 677 threads and a bunch of handles. Handles are just little pointers to objects, like at the early start of this lecture, we had a Windows API call to open a window, and it returns a handle to the window. So the handles are just data objects in the processes in the threads. Right. That's handles. Okay, every thread has many handles, and you can examine the details of every thread in Process Explorer. Although I've never had to do that, you might have to do that to debug complicated software you're writing. You can go into Process Explorer, and you can actually examine the threads here one by one and see all the threads, and they have a number, a thread ID number, and you could go here and try to figure out what they're all doing and say which one is having a bug. All right, let's try another Kahoot. That's this one. All right, so what part of a DIL lists the entry points it provides? Those are the exports. Good. All right, which memory section is a single block in Linux, but many separate pieces in Windows? The heap. Good. All right, which one of these has the largest number of instances when running Windows? Handles. There are many handles per thread, many threads per process, and of course, only a few windows. Some processes open windows, most of them don't. All right. All right, what's the allocation unit for CPU time in Windows? It goes by threads. That's the point. Every thread gets a chance to move, and a lot of threads are in the waiting state, so that's why it lets the threads that can move, while the ones that are waiting wait for something to happen so they can move later. All right. So we'll carry on here. So we can now talk about DCOM. And this explains a lot of how Windows works and why Windows is vulnerable. And the thing is to understand this Microsoft distributed common objects model and distributed computing environment and remote procedure calls. And the fundamental thing about Microsoft, which has been true since Bill Gates was a teenager, is he's a capitalist. Microsoft has always been designed to make money. Right from the beginning, a lot of Linux projects were like idealists that just wanted to save the world or something. Microsoft never was in this except to make money, and that explains how they work. So the point is that if you write software, they want to make it easy to sell that software to be reused under another circumstance by a company. And the idea was you'd have a rich ecosystem of people writing software and selling software and licensing software to each other, so you wouldn't really have to write a whole program. You could buy the components from other people. That's the idea. So you can buy third-party COM modules and just tie them together with Visual Basic to build software. So COM objects are these little pieces of software that can be written in any supported language and interoperate seamlessly. So something written in one language could be operating with something else. Now the problem is you have to define the inputs of it, and that's called the interface description language file. You explain exactly what inputs and outputs are for this piece of software you've written so it can be properly integrated with other pieces. So that looks like this. You've got a structure here with elements in it. You've got a function here that's got a series of things like a string here, and these things are type 1, whatever that is. Here's a handle to something. So you just have a data structure, like a C++ data structure in this file, explaining what the data structures are that come in and out of your software. And so this specifies arguments and return values for a function, and it's defined by this thing called a universally unique identifier or a globally unique identifier, which is a way to identify it, 128 bits long, the same size as an IPv6 address. So you can load a COM object directly into process space as a library, or you can launch it as a service. Running as a service is more stable and secure, but much slower. In-process calls are 1,000 times faster than calling the COM interface on the same machine but in a different process. So the same software can be written for one environment and then reused in another environment. So if you look in the Service Control Manager, you'll see services.exe, and that's the Service Control Manager. So Microsoft wants it easy to write software, and so a simple registry or parameter change tells a program to use a different process or even a different machine. So you can write a program to use something that was in a library attached to this process, and then you could switch it to a service, and then you could even switch it to a library or process running on a different machine easily. And that's the idea. It will get slower, of course, if you're on a different machine on the network, but that might be okay, that might be what you want. So that's remote procedure calls. Remote procedure calls are calling another machine to provide some kind of service, and they're always listening on port TCP 135. So you can look at these remote procedure calls here. It'll make a handshake to 135, and then it will bind and make a mapping request and a mapping response and so on. You can see this traffic. This is why port 135 is the source of a lot of viruses, because the typical port 135 on Windows machines has many, many services on it, many, many RPCs, and some of those may have a bug. It's a lot of software hiding behind there, and any one of them has a flaw like a buffer overflow, then it's a weakness people get in. And so the map request, going to there, will show you something like this. They call it floors. There are 5 floors, which I think are the different services it offers, and it will show you UUID of them, so you can identify them by UUID and hopefully tell which one is the one you want to use. So components will depend on the RPC. So in services, you can look at RPC, and you'll see RPC depends on DCOM and the RPC endpoint mapper, and our DCOM server process launcher depends on all these other things. So there's a whole lot of different components all working together to make anything work in Windows. And so what you can do is you can write code in one environment, and yeah, I have to reconnect this anyway. Might as well do it now. I'll need it for the demo later. Oh, maybe it went to sleep on me. Anyway, we'll get there in a minute. All right, so you can write code like a DIL in your application to do something, and then you can decide, this is great, I want to take this same thing and move it to a service so it can be shared by many machines on the same, on many processes on the same machine, and then I want to share it over the network with RPC. So what happens is code that was never intended to be shared across the network is reused and shared across the network, and this is a lot of where the security problems come in. And it's the way the whole internet worked too. I mean, you had things like Telnet. The original point of Telnet was to have a keyboard connected to a computer in the room, going through a cable in the room, no network at all. So there, nothing was encrypted. It was just moving the key presses from your keyboard to the machine in this room. But then they adapted it to go over the internet. So now you were sending internet traffic that was not encrypted. And that's the kind of thing that happens. You take a local process that might have been reasonably safe in its original environment and lift it into a more dangerous environment where it's unsafe. By the way, the same thing happened with cloud migration. Over the last 10 years, many people have moved their data centers to the cloud, and a great many of them found out that they didn't know how to properly configure their cloud machines, and they ended up exposing all their data to the whole world that used to be relatively safe in their own data center that was not publicly accessible. So anyway, that's the game here. And so there's a bunch of tools to exploit remote procedure call flaws. It is a very common problem. Spike is one of many of the tools that exist just to scan and find vulnerabilities in remote procedure calls. Now, tokens and impersonation are another interesting issue. A token is a 32-bit integer, which is a handle to a data object in memory, and the token identifies who you are. So here is explorer.exe. Somebody is logged into a Windows system, are looking in Process Explorer, and so explorer.exe is what draws the desktop and the icons and everything. And you can see it's running here with this token. It's Sam that is logged in on this machine, and that has just a address here, just a 32-bit address for it. So that is called the token, which determines who is using this process. And you can copy a token to it. So you can launch a process and then copy a token and assign it to a different person. So if you can find an administrator process laying around, you can copy the administrator token down to it and make that process run with administrator rights. That's a common technique, token impersonation. And then there's exception handling. When you have something illegal happen, like a divide by zero or an attempt to execute memory that is not allocated for the use of this process, or an attempt to go to an invalid memory location, or a user land process trying to execute a kernel land instruction, this causes an exception. For some reason, it cannot be done, so it passes to the exception handler. The exception handler is a place where you can specify what to happen when an exception happens. So if you're a good programmer, you consider all the exceptions and you carefully write code to do something intelligent with the exceptions. If you're a bad programmer, you fail to handle the exception, and then the program will crash and just pop up a Microsoft Windows default box saying this process has crashed. Would you like to relaunch it or debug it? Something like that. If it's in the kernel, you get the blue screen of death. The machine dies. The application, a more professionally written application, would specify custom exception handlers to avoid crashing. And so you can see them in the Immunity Debugger. It's a area of memory, and you'll see a structured exception handler chain. This is a series of addresses. So it will take the exception and pass it to this code, and that code can try to read the exception identifier and see if it can process it, and then it'll try a next one. And if none of the ones in the exception handler thread, exception handler chain, handle it, then it goes to the operating system to have some kind of default message about how your program died. So if you can alter the exception handler chain, which is addresses in memory, then you can control the execution of the box by modifying the exception handler and then causing an exception, and then it will execute the code you put in there. It will move to the address you put in there. So you can do all this with debuggers. Soft Ice is old, pretty much gone. WinDebug is the most powerful one, written by Microsoft. It is very hard to use. We aren't going to use it later, but you don't start with it. In fact, I don't think we're going to use it in this course. We're going to use it in the malware analysis course to do kernel debugging. Ollie Debug is very popular, but apparently abandoned. But it set the standard for the user interface. And from Ollie Debug, Immunity Debugger bought the Ollie Debug software and kept developing it, so it's somewhat better, very much similar. And now there's one called X64 Debug and X32 Debug, which can handle 64 and 32-bit code and look almost identical and run almost identical, that are open source. So we'll use Immunity today, but you can use any of these Windows debuggers pretty interchangeably. All right. So the main thing you do when you open it, you see on the top left, you see assembly code showing the instructions that are got to be processed. On the top right, you see the registers like the extended instruction pointer and ESP and EBP. The stack is here, showing addresses and sometimes identifiers to show you what the addresses point to. And here's a hex dump pane where you can dump any region of memory and see it in hex and ASCII. Yeah, X64 Debug is the newest one of those, yeah. All right. And they all work very much the same. If you know how to use Ollie, you pretty much know how to use all the rest. All right, so let's try the last Kahoot, which is here. All right. All right, so which file has the inputs and outputs of an object? That's it, interface description object, interface description language, something like that. That's the file for a COM object. Which one of these is 128 bits long? Universally unique identifier, okay? All right, which structure is used when a division by zero occurs? That's an exception, so it goes to the structured exception handler. All right, which one listens on port 135? Remote procedure calls, all right. So one machine can request service from some process running on a different machine. Which one of these is 32 bits long? The token. All right, it identifies who is running a process and therefore what privileges they have. All right, which debugger can debug the kernel? Only WinDebug. Okay. All right. Good. I'm going to stop the recording.